Hello everyone, good evening. So welcome to the session 8 of system of particles and rotation motion. So today what we are going to do is we will continue our discussion about the moment of inertia. Already in the previous session what we were doing, so we were looking at some standard shapes of the objects and we were trying to calculate moment of inertia for the standard shapes. Like if you recall, right? So we have talked about what is the moment of inertia of a rod, about the axis passing through end of the rod as well as about an axis passing through the center of mass of the rod or the midpoint of the rod. Okay, then we talked about the moment of inertia of the ring about the principal axis. Then we talked about the moment of inertia of the hollow pipe about the principal axis. Then we talked about the moment of inertia of the disc. Now today we will start with the other common shapes. Okay, so the first one that we will begin with is the moment of inertia of a solid cylinder. So what is a solid cylinder? The difference between the hollow cylinder and solid cylinder is what? In a solid cylinder, right, mass will be in the entire volume of the cylinder. In a solid cylinder, mass will be in the entire volume of the cylinder. So here look at this, we are trying to find the moment of inertia of the solid cylinder about the axis passing through the center of its circular face and parallel to the length. Means what? This is the axis we are talking about. The axis is what? Passing through the center of the circular face and which is parallel to the length. So that is what even in the case of the hollow pipe also we have chosen the same axis, right? In fact, this axis is what we will generally be calling as the principal axis. Okay. Now how we will have to find the moment of inertia of the cylinder. So here we will consider the cylinder to be having a mass m, radius r, and cylinder will have one more geometric property. What is it? Height of the cylinder. Okay, so we will consider that the mass of the cylinder is m, radius of the cylinder is r, and height of the cylinder is what? H. So here we need to find the moment of inertia of this solid cylinder about the principal axis. For this what we will do is like the way if you have remember the previous the moment of inertia of the hollow pipe. So what is it that we have considered there? If you have a pile up of rings like this, if you have one ring arranged, the pile up of rings, right? The pile up of rings is what is going to give us a hollow pipe. If you pile up one ring like that, that is going to give us what? Hollow pipe. Now if we have pile up of discs, so if you have the pile up of discs, right, what is it going to give us? Like one disc, then another disc, like that. If you arrange, what we are going to get? You can check it, right? So if you keep disc by disc, what we are going to get? We are going to get this solid cylinder. Okay, so what we will do is we take like one small disc, take a small disc of mass dm, because the pile up of discs is what is going to give us the solid cylinder, right? Take a small disc of mass what? Dm. It will be somewhere because it is a collection of discs one by one, right? Now for this disc, what is the axis we are choosing? It is the principal axis because it will be what? The axis passing through the center of the disc and perpendicular to the plane of the disc. Already we have the disc result, right? What is the moment of inertia of this small disc? It will be what? Mass of the disc, which is dm, into square of the radius by 2. That is the formula, right? The moment of inertia of the disc about the principal axis is what? Mass of the disc times square of the radius by 2. Now if you want to find moment of inertia of the entire solid cylinder, means what? Because it is a pile up of discs. Now you see one thing, for each and every disc, right, the r value is same for every disc because they will have the same radius, right? Then only we will get the, so here we are, cylinder means what? Throughout the radius, circular face radius will be same. Okay, now if you want to find the overall moment of inertia, means what? We have to integrate this. So we have taken a small part of the cylinder, solid cylinder. We have written the moment of inertia expression for that. Now we have to integrate it. When we are integrating it, right, remember that is what we just mentioned before, right? For every such a small disk you take, r is a constant. Means in this integration, r square by 2 will become like a constant term that can be taken out. So what is left out? What is left out here? Just this integral dm is left out. What is left out here? Just this integral dm, right? So what is integral dm means? We are like integration is summation only, right? We are integrating all these disk masses. So small disk masses, when we integrate it, what we are going to get? We are going to get the total mass of the solid cylinder. We are going to get the total mass of the solid cylinder, correct? So this integration is going to give us the mass of the solid cylinder m. Already there is r square by 2 which will be just like that. So the thing is, we have seen what is the moment of inertia of the disk about its principal axis. What is the value? mr square by 2. Now we are seeing what is the moment of inertia of a solid cylinder about the principal axis. For this also the value is same, mr square by 2. You can even see one thing. This moment of inertia value does not depend upon the height of the cylinder or the length of the cylinder. So generally, either we will say height h of the cylinder or length L. Okay. So here you can see this moment of inertia value does not depend upon the height of the cylinder or the length of the cylinder. Okay. So this is about the moment of inertia of the solid cylinder about the principal axis. Now we will go into the next shapes. A rectangular lamina. A special case of this will be a square. So rectangle means what? Like you have, it's not rectangle, it's a rectangular lamina. Lamina means the mass is it's a two-dimensional shape. So when we use the word lamina means what? It is a 2D shape. Okay. So mass is like we have a rectangular sheet, iron sheet or something like that. That is what is the rectangular lamina. Okay. Now we have to find the moment of inertia of the rectangular lamina. Here you can see they have given us the geometrical dimensions. A and B are the geometrical dimensions. So we will say m is the mass of the rectangular lamina. We will say m is the mass of the rectangular lamina, and the geometrical dimensions are what? A and B. Okay. Now we need to find moment of inertia of the rectangular lamina about an axis passing through one of its sides. So what is the axis we are going to choose here? We are going to choose the axis that is passing through one of the sides. Means how we can take it? First we will consider the axis. Let us say we are taking the axis passing through the side B. What is this? It is the axis passing through side B. Okay, so this is the axis we are choosing. Now for this axis, right, we will have to find the moment of inertia. The thing is, if you look at this rectangular lamina, the rectangular lamina can be divided as very small segments. As you can see, because the axis is like this, I am dividing the rectangular lamina into very small segments. You can see one thing. If I am just coloring one of these segments, look at this, I will color one of the segment. Okay, so if I color one of the segment, this segment, right, is like, how is it? It's like a rod, isn't it? It's like a rod of length A, because our axis is what? Axis which is passing through side B. So if you divide this lamina into that small portions, which is each of them is like what? It's like a rod. Okay. Now each of these rods will be having a length A. Each of these rods will be having a length A. Okay. Now let us say the mass of this is because we'll take a small element only, right? dm. For this rod, it's like a rod. What is the axis? The axis is like an axis passing through end of the rod and perpendicular to the length of the rod. Okay. So for this, what is the small element? It's like a rod. the moment of inertia of the small element will be what? Mass of this rod, which is dm, into square of its length by 3. Because for a rod of mass m and length L, if you have an axis passing through end of the rod and perpendicular to the length of the rod, right, what is the moment of inertia value? ml square by 3, right? So same formula we are using here. We are using the same formula. This is the moment of inertia for that small portion. Now the thing is, you take any such portion, that the second portion I have colored it just now, right? That is also like a rod only, right? What is the length of this one? A. The length of this portion is also what? A, right? Which means what? If you are trying to find the overall moment of inertia by integrating it, here 3 is anyway constant only, right? The A also will be constant for each and every, like you take an element here. For this also the A square, so A square will come in each and every case, which means what? The A square by 3 overall is like a constant, it comes out. Then what is the remaining thing? Integral dm, right? Integral dm means what? Dm is the mass of that small rod like element. If you integrate it, means we are trying to sum it up. Integration is summation only, right? If you sum up the mass of all these small elements, what we are going to get? We will get what is the mass of the overall lamina, which is what? Which is our capital M. Correct. So what is the answer for this? It will be what? M into, so if you conclude the integration means we will get M, right? So it will be what? M into A square by 3. What is it? M into A square by 3. So if you take an axis which is passing through the side B, if you take an axis passing through side B, then what will be the moment of inertia of the lamina about that axis? It will be what? M into A square by 3. Now we can tell one thing easily, right? Because we didn't fix on A or B, anything like that, right? If the axis passes through side A, so the axis, so this is what, when we are choosing the axis passing through side B, right? The axis is passing through side B. So what is the moment of inertia value? M into A square by 3. Now what we are doing is we are saying, let us consider the axis which is passing through side A. We will consider the axis passing through side A and we will see the result. Then we will tell what is the general concept. Okay. So here look at this. I am choosing the axis like this. This is the axis passing through side A. Okay. Now this is our rotational axis. Here what we will do is we will try to divide the lamina into thin elements. Each of these elements is like a rod. You can see here how I am dividing it. The way I am dividing it, right? You see any small portion. You see any small portion. This is like what? It is like a, how is it? It is like a rod of mass. If you take dm, small element, length will be equal to what? What is this length? B. So as it is, if you go for the integration, right? Remember what we are going to get? So for this element, what is it? dm into B square by 3, because it is like what? Axis passing through end of the rod and perpendicular to the length. If you integrate it, means we will get the overall moment of inertia. For any element you take, the length of the element will be only what? B. So B square by 3 will come out. Integral dm means what? It will be m. So what will be the answer? It will be what? mb square by 3. Okay. So if you have the axis passing through side B, then what is the value? It will be ma square by 3. Okay. If you have the axis passing through side A, then what is the moment of inertia value? mb square by 3. Okay. So we will just note it down so that because in that formula, right, the other side will come, because when we divide the lamina into small rod like elements. Okay. So what we are going to get? We will get that each of the element is like a rod of length which is equal to the other side length. Okay, so if axis passes through side B, that is what we did before. First, what is the moment of inertia value? ma square by 3, mass into square of the other side divided by 3. Okay, so next look at it. If axis passes through side A, if the axis is passing through side A, right, that is the second one we did. Okay, so what is the moment of inertia value? mb square by 3. What is the moment of inertia value? It is what? M into b square by 3. Okay, so this is how we will have the moment of inertia of a rectangular lamina when the axis is passing through one of its sides. Okay, so we'll just make a note of it. Then the next scenario is same concept, rectangular lamina, but the axis is passing through its center of mass and parallel to its side. The axis is what? Passing through center of mass. So center of mass means what? We are taking an uniform lamina, means it will be the geometric center. Okay, so we will first take axis passing through the center of mass and parallel to the side B. So here again we will say mass of the lamina is m. Now again similar concept will be working here. What is it? We will divide the lamina into small elements, thin elements. Each of these elements will be like a rod. Each of these elements will be like a rod. Look at this now. If you take a small portion of this, okay, so let us say the mass of this is dm. What is the length of this? The length of this will be the length of the other side, which is a. Correct. So look at this length from here to here. What is it? That is the a value, right? If you take the axis which is parallel to the side B, then you know the length of the element will be what? Side length a. Here if you see the axis, right, is like what? An axis which is passing through the midpoint of the rod. Like this element is like a rod. The axis is like what? It is an axis passing through midpoint of the rod and perpendicular to the length of the rod. Correct. So what will be the moment of inertia of this rod? It's a differential rod element. That is what we can call it. Okay, so for the differential rod element, what is the small moment of inertia? It will be what? Mass of this rod element into square of the length divided by 12. Remember, for a rod of mass m and length L, if you have the axis passing through the center of mass and perpendicular to the length of the rod, right, what is the moment of inertia value? ml square by 12. What is the moment of inertia value? It is what? ml square by 12. Correct. So here it will be what? The mass of the element dm into a square by 12 will come. Okay. Now if you look at any such rod element, right, you take another rod element also. You take another rod element here. Okay, so for all of them, what is the length here? Length will be a only, right? So in each and every such expression, this a square is going to keep coming. So if you want to integrate, it means this a square by 12 will be a constant. A square by 12 will be a constant, right? That just comes out. Integral dm will be there. What is integral dm means? If you add up all these differential rod elements, we will get the mass of the overall lamina, right? Okay, so look at this. What is the moment of inertia value here? Mass of the rectangular lamina into a square by 12. We will see that analogy, right? Like, you know, in the previous case, what we were getting, if the axis is passing through side B, then you know what is the answer we had? M into a square by 3. Here if the axis is passing through center of mass and parallel to side B, right, then what is the moment of inertia value? M into a square by 12. What is it? M into a square by 12. Now without doing the proof also, we can tell the other result. What will be the other result? If the axis is passing through center of mass and parallel to side A, you can tell yourself, right? So what will be the answer? If you have the axis passing through the center of mass and parallel to side A, you take the axis, means the moment of inertia value will be equal to what? It will be m into b square by 12 will come. Okay, so it will be what, m into b square by 12. Okay, so this is about the moment of inertia of the rectangular lamina. Okay, now I said square is a special case of rectangular lamina. How? A will be equal to B, that's it. Square is nothing but what? It is a special case of the rectangular lamina, right? So in that case A will be equal to B. Okay, now here we are trying to find the moment of inertia of for a ring we have found the moment of inertia about one axis, that is the axis passing through the center of the ring and perpendicular to the plane formed by the ring. Similarly for the disc also, we have found moment of inertia with respect to what we were calling as the principal axis. What is the principal axis? It is the axis passing through the center of the disc and perpendicular to the plane of the disc, correct? Now the axis can be anything, right? Because there is no fixed thing like, okay, you have to have only this as the axis. Then you know why we are not finding moment of inertia about each and every axis. In fact, it will be too difficult, right? So if we sit down to find moment of inertia for each and every axis, in fact, when we were doing the integration and all this, right, it is relatively simpler because we had symmetry. But not every case we will have symmetry. If you take axis which is randomly positioned, we will not have the symmetry help. But then there are some theorems, so which we call as a theorems of moment of inertia. In fact, we might expect some questions straight also sometimes based on these theorems in the JEE mains level. Okay, so these theorems of moment of inertia, they will actually help us if we know the moment of inertia with respect to one axis, like for at least the common shapes, right? We were trying to find the moment of inertia with respect to one standard axis, like disc or a ring or a cylinder. We were in fact calling it as what? Principal axis, like that. Okay, we will try to see how the theorems of moment of inertia can actually help us to find the moment of inertia about the other, because the moment of inertia value with respect to principal axis. Let us talk about the disc case. Using this, how we will be able to find the moment of inertia with respect to any other axis? Like somebody is suddenly giving us, okay, find the moment of inertia about this axis. So using these theorems, right, we will be able to find out. I mean, it is not possible in each and every case, but in some select cases, select examples, using these theorems, we can find the moment of inertia about any unknown axis. That is the main purpose of the theorems. Okay. Now there are two theorems. One is what we call as the parallel axis theorem. So for this, we'll just look at the result. Okay. So we'll make a separate video on the derivation for the parallel axis theorem. So parallel axis theorem is a very important one because this can be used for any shaped object. Meaning what? Like when we talk about the objects, right, generally we will talk about a 1D object like a rod. I mean, usually nothing is 1D, right, because whenever we say object means it occupies some volume, that we know. But if you take a rod means, what is our general understanding? Okay, so we can consider that the mass is on, if you say a rod means what we generally consider, okay, the mass is probably along that one direction. So we will take it as what? Almost like a 1D shape. But nothing is really 1D, okay? Or you have a, like this, the previous example, right, the lamina, that is the best one, a disc. All these are what? 2D shapes. They will have a surface. So mass will be on the surface. And then we have the, this can be a general object. Okay, so general objects will be what? You take a solid cylinder. Next we will see spheres, solid sphere, or in general, like you can see an object here, right? This is also like it's a 3D object which occupies some volume. Now the parallel axis theorem, right, can be used for any type of object, whether the object may be a 1D object or a 2D or a 3D. It can be used for any type of object. Okay, so that is the importance of the parallel axis theorem. So what is this parallel axis theorem? Like, you know, we take an axis. The axis can be anywhere. Okay, let us say the moment of inertia about this axis is I. What is the moment of inertia about the axis? We will say it is I. Okay, now just parallel to that axis, we have to draw an axis which is just parallel to that and passing through the center of mass. Look at this. What is this? This is an axis which is parallel to the axis that we initially marked, correct? And that is passing through center of mass. The moment of inertia with respect to this one, this is also we will generally call as center of mass axis, like that, because it passes through center of mass. The moment of inertia about this axis, we will call it as ICM. The moment of inertia about the center of mass axis, let us call it as what? ICM. Okay. Now the parallel axis theorem final conclusion, or you know, the final result is the moment of inertia of the object about the axis we have chosen, right, I. The value will be equal to I with respect to center of mass axis plus, if this object is having a mass m, mass of the object times r square. So here, you know, don't think r is radius or anything, because this, as we said, can be used for any and every object, right? So r is not a radius or anything. R is the perpendicular distance between the two axes. What is in this case r? R is what? The perpendicular distance between the two axes. The axis that is the parallel axis we are choosing, right? The perpendicular distance between them is what? R. Okay, so this is what is the final conclusion or the final result of the parallel axis theorem. In a separate video, as I said, right, we will even see how this result actually comes. But what we will do now is we will just go through some of the other aspects related to the parallel axis theorem. Okay, so look at this. If you have an object like this one, or you have an object like this, you can think about many parallel axes, like, you know, for the object A, axis 1, axis 2, axis 3, or what? Parallel axis. You see here axis 2 is passing through the center of mass, which is what? That ICM. Now if this distance is R1, I1 will be equal to what? ICM plus, if m is the mass of the object, means m into R1 square. Similarly, if this distance is R2, this distance is R2, right, then I2, moment of inertia, not I2, I3, okay, the moment of inertia with respect to the axis 3 will be equal to what? I center of mass plus m into the R2 square. Correct. Distance between the two parallel axes is what? R2 here. So the idea is, you take a set of parallel axes. Among them, if one of them is passing through exactly center of mass, then the moment of inertia value with respect to that axis will be the least of them. Why? Because you see any other moment of inertia, right, it will be what? ICM plus something will come. You see moment of inertia about any other axis, it will be what? ICM plus some value will come, right? So which means what? Among the parallel lines that you can think of, or parallel axis you can think of, the one that passes through center of mass will have the least moment of inertia, which means in this case, right, if you look at object B, here you see that axis 5 is passing through center of mass, which means what? The moment of inertia with respect to axis 5 will be less than axis 4, and axis 5 will be less than also axis 6. Why? Because among all the parallel axes, we may not be able to straight away compare all the parallel axes. If you know the distances and all, that means we can even compare that. I mean, that probably we will see in some examples where we have comparison of the moment of inertia. But here the thing is, if you are drawing parallel axis, means the one that passes through center of mass. that is going to have the least moment of inertia among all the parallel axes. Okay. Now we'll even try to check, because we have given the formula. What is the formula? We said I is equal to ICM plus M into R square. What is this R here? The perpendicular distance between the two parallel axes. We will try to verify. Okay. We will verify by using a result that we already know. Okay, so let us not try and take some other things. Let us take an example that we already know about. Okay, so here we will take a rod of mass M and length L. Okay, we will mark an axis passing through end of the rod and perpendicular to the length of the rod. The moment of inertia with respect to that axis is, let us call it as I. Already we know the value of that, right? What is it? ml square by 3. Correct. Now we will draw an axis which is parallel to that and passing through the center of mass. This moment of inertia value will be what? ICM. This also we know. What is ICM value? Moment of inertia of a rod about the axis passing through the midpoint of the rod and perpendicular to the length of the rod. What is it? ml square by 12. Now what is the distance between the two parallel lines? It is what? L by 2. Now we will verify. Okay, what is the thing we have? I is on the left side, right? What is the I value? Already we have. Let us try to verify. ml square by 3 is I value. Right side, what is there? ICM, which is ml square by 12 plus mass of the object times square R square, right? Because R is what? The perpendicular distance between the two parallel lines. In this case, what is it? L by 2. So m into L by 2 the square, which means what? L square by 4. So add them up. 12 is the LCM. Correct. So it will be what? 3ml square plus ml square. Okay. So what is it? 4ml square by 12. What is 4ml square by 12 means? 4 1s are 4 3s are, right? What is it? Finally, what we are getting in the RHS also? ml square by 3. Check it. So we already know what is the moment of inertia about the axis passing through end of the rod and perpendicular to the length of the rod. That we know, right? ml square by 3. We are trying to verify whether this parallax theorem is able to adjust these values. So now we are able to clearly see, right? Because whatever the result that we already have, they are fitting into the parallax theorem result. Okay, and parallax theorem, one thing is what? So why I am mentioning it is, when we go to the other theorem, right, there will be some limitations on when we can use that other theorem. But parallax theorem, there is no limit like that. Parallax theorem can be used for any and every type of object, whether the object is a 1D object or a 2D object. It can be used for any and every object. Okay. Now we will come to the second one. What is second one? The perpendicular axis theorem. So here we will see the result. First, the perpendicular axis theorem, right, can be used only for two-dimensional shapes. 3D shapes, no. The perpendicular axis theorem cannot be used for the 3D shapes. The perpendicular axis theorem cannot be used for the 3D shapes. Okay. So if you have a 2D shape, it will be like what? Surface object, right? Like a lamina, rectangular lamina, or a disc like that. Okay. If you have a 2D shape, you think about a line which we can call it as say x-axis, and another axis which we can call as y-axis. Both will be what? We know that they will be what? First of all, perpendicular to each other. X and Y are the axes which are in the plane. Because a 2D object means what? It will have a plane, right? X and Y are what? The axes which are in the plane, but they will be perpendicular. They will have a point of intersection, right? Because if you have two lines which are not parallel, when they are in a plane means they will definitely intersect at a point. From that point of intersection, draw an axis which is perpendicular to the plane. That we call as z-axis. Okay. So the outcome of the perpendicular axis theorem is that the moment of inertia of the body with respect to x-axis plus with respect to y-axis, the two perpendicular axes we are taking, which will be in the plane, that is our ix and iy. When you sum it up, that will be equal to what? Iz. What is Iz? The moment of inertia of the planar body with respect to axis which is passing through the point of intersection of these two. That is important. You can't take a z-axis here. It should pass through the point of intersection and perpendicular to the plane of the sheet. Okay. So this is the final result of the perpendicular axis theorem. Now we will see how this comes, because we have seen the result. And now you can understand why we have been mentioning that this is only for the 2D objects. This will be only for what? 2D, because the way we have defined itself, right, is we have said, it's a plane sheet. In that you are choosing two axes, x-axis, y-axis, which will be perpendicular. Z is what? That will be passing through the point of intersection of x and y and perpendicular to the plane of the object, because the object we are choosing here is what? It's a lamina object or a 2D object. Okay. Now we will see how this result comes. So this one we will quickly try to prove also. The thing is, if you have imagine we are seeing the top view, like this is the sheet we are seeing from the top. So you can see the z-axis is what? We can't represent on a 2D page, right? Z-axis will be, it's like what? Coming towards us. Okay. Now you take a small element of the object. The element is having a mass dm, differential element. What is the distance of this from the x-axis? It will be what? The y coordinate. What will be the distance of this element from the x-axis? Will be what? Y coordinate. So the small element moment of inertia with respect to x-axis will be what? Dm into y square. Now the same small element, we will see what is the distance from the y-axis. It will be what? The x coordinate. So if you look at what is the moment of inertia of the small element with respect to y-axis, it will be what? Mass of the element into square of the x coordinate. Why? Because the distance of the small, you take up at this point P, we take a small element, right? The distance of the point from the x-axis is what? Y coordinate. The distance of the point from the y-axis is what? X coordinate. Because for a particle, right, what is the moment of inertia? If we choose an axis means what is the moment of inertia? Mass of the particle times square of the distance from the axis, right? Mass of the particle times square of the distance from the axis. Okay. Now what will be the moment of inertia of that small element with respect to z-axis? You see here this r is the distance from the z-axis. This r is the distance from the z-axis. Look at this now. If you carefully observe it, what we are going to get? This r. So z-axis is like, it is perpendicular to the plane. Okay. The distance r, right, from this right angle triangle, r square will be equal to what? X square plus y square, because that is the hypotenuse, right? The small element moment of inertia with respect to z-axis is what? Dm into r square. But what is r square? Dm into x square plus y square. That is coming from the Pythagoras theorem. Correct. So if you just look at these three values, we have taken we said any general point of the object, right? When we say a point P means we have not fixed anything. We said general point. For the general point, look at this. The moment of inertia with respect to the z-axis, it will be what? If you split them, means what we will get? dm into x square plus dm into y square, right? Which is what? The small element moment of inertia with respect to x-axis plus the small element moment of inertia with respect to y-axis. Now if you generally say integrate it, means if you integrate, left hand side is what? The moment of inertia of the entire body with respect to z-axis is equal to what? Ix plus Iy. Okay, so for each and every small element also, that relation will be satisfied, right? That's why, when you integrate it, means what we will get, because for any element, we are choosing general element, right? That is satisfying the relation. Means for any element, the relation will be satisfied. So what is the final conclusion? Iz will be equal to what? Ix plus Iy. Okay, so this is what is the perpendicular axis theorem, and when we can use it? We can only use it because if it is not a 2D shape, right? All the elements will not be on the surface. Understand this. Why? If it is not a 2D shape, means here this result, right? This r square is equal to x square plus y square will be true when all the particles are on that same surface. When all the particles are on the same surface, right? If all the particles are not on the surface, then this result will not be valid. That's why this perpendicular axis theorem is only for what? 2D objects. It's not for the 3D objects. Okay. Now we'll see, how using these theorems, right, we can find the moment of inertia value of a ring, because already ring we have discussed with respect to principal axis. What is the moment of inertia? So if you take a ring of mass m and radius r, what is the moment of inertia with respect to the principal axis? It is what? mr square, right? What is principal axis of the ring? It is an axis which is passing through center of the ring and perpendicular to the plane of the ring, correct? Now we will have to find what is the moment of inertia of the ring about its diameter. Diameter means what? It will be, where it will be? It will be in the plane of the ring. See, how do we get the clue that which theorem to use? This is important. What we know about the ring, just think about it. What we know about the ring, we know the moment of inertia about the axis which is passing through the center of mass of the ring and perpendicular to the plane. This is what is our principal axis, correct? Diameter means which is in the plane. We know the moment of inertia value of the axis which is perpendicular to the plane. So now we will have the hint, right? So what is the theorem that we can think of? Because the moment of inertia we know is about the axis which is perpendicular to the plane. The moment of inertia we have to find is about the axis which is in the plane. So the theorem that we need to think of is what? Perpendicular axis theorem. Now how we are going to use it? Because for the perpendicular axis theorem we have to have Ix and Iy, right? Let us say we want to find the moment of inertia with respect to the diameter 1. You have to take one more axis which is in the plane. We have to take one more axis which is in the plane that is perpendicular to this. If this is like an Ix, means that is like what? Iy. By the way, that is also a diameter only. If you draw one more line which is perpendicular to the diameter 1, means what? That is also diameter, correct? Let us call it as diameter 2. Now what is the perpendicular axis theorem statement? The Iz value is equal to what? Ix plus Iy, correct? So Iz value we know, moment of inertia with respect to the principal axis. What is it? mr square is equal to what? Ix plus Iy. Ix means we are saying moment of inertia about the diameter 1. Iz is what? Moment of inertia. Sorry, Iy is what? Moment of inertia with respect to diameter 2. Now for a ring, both the diameters are what? Symmetrical, right? Whatever the, so if the ring is rotating about diameter 1 or if the ring is rotating about diameter 2, both are symmetrical, right? Means what? The I1 value must be equal to I2. I1 value will be equal to what? I2. So we can say what? In place of I2 also we can put I1. So what we will get? mr square is equal to I1 plus another I1, that is what, 2 times I1. Okay, so straight away what we will get from here, mr square by 2 is equal to I1, and that will be of course equal to I2. So moment of inertia of a ring about its diameter is what, here which theorem we are using? We are using the perpendicular axis theorem. So what is the moment of inertia of the ring about the diameter? It is what, mr square by 2. Now we will see moment of inertia of a ring about the tangential axis which is in its own plane. Means this is what, this is a tangent which is in the plane of the ring. Definitely tangent means what, it will be passing through the boundary, right? Think of it. We know the moment of inertia of the ring about the diameter. Okay, so if you can draw a diameter which is parallel to this, that will be like our ICM. Because if you draw a diameter which is parallel to this tangent which is in the plane of the ring, the tangent is also in the plane. You draw a diameter parallel to this tangent. This will be like our ICM. This is like our I. What is the distance between these two axes? Radius. What is the parallax theorem? I is equal to what? ICM plus mass of the ring, let's say m, into r square. R is the radius. That is the perpendicular distance between the two parallel axes, right? That is the concept of parallax theorem. But do we know ICM? That is what, moment of inertia of the ring about the diameter, right? What is the value? Just now only we saw, right? What is it? mr square by 2. Just put it. What is it? 3 by 2 mr square. So moment of inertia of a ring about a tangential axis which is in its own plane. The tangent which is in the plane of the ring. What is it? mr square into 3 by 2, or we can say 3 by 2 into mr square. Okay. Now we'll go to one more case. Moment of inertia of the ring about the tangential axis only, this also, but perpendicular to its own plane. Look at this. If you draw a axis which is parallel to this and passing through the center of mass, you know what this is? This we'll call as center of mass axis, but that is actually our principal axis, correct? An axis is passing through center of the ring and perpendicular to the plane of the ring, right? What is it? Is the principal axis. Now you look at this. What is the distance between them? R. What is the parallax theorem concept? I is equal to ICM plus mr square, correct? But what is ICM here? The moment of inertia with respect to the principal axis of the ring. What is the principal axis of the ring moment of inertia? mr square. Another mr square. What is it? 2 times mr square. So if you have a tangent to the ring, but this should be perpendicular to the plane. The tangent should be perpendicular, because tangent means what? Any line that touches is called as a tangent. Previously what we discussed is tangent which is in the plane of the ring. Now what we are discussing is a tangent which is perpendicular to the plane of the ring. Okay. So like this we can see the applications of the parallel axis theorem and the perpendicular axis theorem. Okay. Now we can see one more important result. The moment of inertia of the rectangular lamina. Here the dimensions are given as what? Length is L and breadth is B. We will say mass of the lamina is M. The moment of inertia of the rectangular lamina about an axis passing through the center of mass and perpendicular to its plane. Think of it. So this is like the what? Z axis, right? If you can take two axes like, you know, IX and IY. You see here, what is this x-axis is what? This is the x-axis, right? X-axis is an axis which is what? In the plane of the lamina, parallel to, and that is passing through the center of mass. That is passing through the center of mass, okay? This is what? It's a line which is parallel to length L. So moment of inertia about this axis will be what? M into b square by 12 will come. Remember, we have got this result. If the axis is passing through center of mass of the lamina and parallel to side length L, means moment of inertia will be what? M into b square by 12. Now look at this one. Now this y-axis is what? It is parallel to side B. So moment of inertia will be what? M into L square by 12 will come in that case. Okay. Now what is the axis for which we have to find the moment of inertia? That is our z-axis. So what is the perpendicular? We can use the perpendicular axis theorem, right? Because it is a lamina 2D shaped. What is it? Iz is equal to Ix plus Iy. What is it? M into b square by 12 plus M into L square by 12. What is it? M into b square plus L square whole divided by 12. What is the answer? It will be what? M into b square plus L square whole divided by 12. See, you will take some time. It's not like, in one day we will be able to remember all these results and all that. Okay. At least we'll keep making effort so that, over a period of time, right, we will be able to remember almost all the standard moment of inertia of the common shapes. Other than that, if something is required, means always we can use the parallel axis theorem or the perpendicular axis theorem and then try to find it out. Okay. Now for the objects. Okay, so because we are going to see, just now we have started, we have spent some time on the moment of inertia, but still it is like, we are in the initial discussion itself. We will have to see some more results. If you look at any general object, we choose an axis and we will calculate the moment of inertia. If we replace the entire object, let's say this is the object, we replace the entire object by a particle of same mass. We replace the entire object by a particle of what? Same mass. And keep this at a distance k from the axis. Keep this at a distance k from the axis. If the moment of inertia of this particle, what is the moment of inertia of the particle? Mk square, right? If it is equal to the moment of inertia of the object, then this k is going to be called as what? Radius of gyration. It's a very simple thing. Okay. So you have an axis, so you have a body. The body will have a mass. If you find the moment of inertia of the body or the object about the axis, we'll, depending upon what is the axis, we'll keep getting different values for the moment of inertia. Now, if you are just replacing that object by a single mass, you have to keep this at a distance k from the axis. Then moment of inertia of the particle will be what? M into k square. If that is equal to the moment of inertia of the body with respect to the axis, then this k value is going to be called as what? The radius of gyration. So look at this. Radius of gyration of a body about the axis is the effective distance from the axis where the whole mass can be assumed to be concentrated. Means we just take the entire object and keep this at a single point particle, and the moment of inertia of the single particle will be same as the moment of inertia of the entire object. So at what effective distance we have to keep that single particle? At what effective distance we have to keep that single particle? That is what we will be calling as the radius of gyration. That's what we will be calling as what? Radius of gyration. In fact, no, even some of the past year JEE mains also, you can see some questions have come on the radius of gyration part. Okay. So we'll see one small example and then we'll probably wind up for today. The example on the radius of gyration. Okay. The question is, for a ring of mass m and radius r, what is the radius of gyration for an axis tangential to the ring and in the plane of the ring. See, why I am choosing this example is just now only we did it right. So you have a ring of mass m and radius r. We take a tangent, which is what? A tangent which is in the plane of the ring. What is the moment of inertia of the ring about this tangent? Already we have the result. What is it? 3 by 2 mr square. 3 by 2 mr square, right? Now they are asking what is the radius of gyration. What is the concept? The moment of inertia of the body about the axis. This is the I object. We will say simply equal to what? We replace the entire ring by one single particle of mass m and keep this particular distance k. What is the moment of inertia of the particle? M into k square, right? So simply equate both of them. M gets cancelled. Then what do we have? Take a square root. Root 3 by 2. Root of 3 by 2 into r. That is our k. So check it. What is the radius of gyration value? It is what? Root 3 by 2 into r. So the thing is, it's not like for an object radius of gyration is fixed or anything. Radius of gyration of course depends upon what? It depends upon what is the axis of rotation. Radius of gyration depends upon what is the axis of rotation. Okay. So maybe in your books that you are practicing from, you can also check there are more problems on the radius of gyration. Okay. So probably we will also solve some more questions as we go on, but you can also check. Okay. So this is about the concept radius of gyration. And with this we will hold for today. In the next class, right, we will start discussing about some more common shapes, because we have still not covered sphere, then there is a cone, things are left. Okay. And we will also solve some miscellaneous questions in the moment of inertia concept. Okay. So we will see in the next class.